Hello, this is my recording for Lab 1A. So currently I'm showing you my main.c file. At the top here is a typedef I made, which is where I specify the instruction type for table 1b, which is where we call test_var for different functions. And basically right here is where I define the type of instruction, and var.type, as you can see in the highlighted, is basically a variable that stays for all the test functions. And this is the way I'm able to quickly test var_type for different data types. So here's my void.main. Here is where all the GPIO pins are set. In my while loop, I have three main if conditions. My first one is basically checking if the cycle of counting to 15 in LEDs is ran, and if it's ran less than 3 times, it'll continue to run and cycle over counting LEDs. And once it's ran the third time, I'm basically resetting all the pins back to 0, and then every additional execution of the count cycle will basically run the test function where the PC0 is turned on, the test function is ran, and then the pin is turned off. And if we go to this test function, here is the var type again for test var, and this line 82 is where I would set the equation. So now what I'm going to do is run this currently, the code with test var equal to num as the test case, and I'm going to maintain unit8_t as my var type. So what I'm going to do is hit run here and transfer over to the LED. This is my test setup, and as you'll see, we're going to cycle through the 16. So 1, 2, and 3. And sorry, that was 15, not 16 counts. And after it's finished 3 iterations of counting to 15, you'll notice PC0, which is the least significant bit LED, is on, and same with PC1. So now if we go over to the oscilloscope, which I'm using the 82 Discovery analog, I'll hit run just to show, and the blue, which is channel 1, is PC0, and the pinkish purple is channel 2, which is PC1. These red lines are my cursors, and as you can see here, the delta X is the time delay. So what I'm going to do now is stop it to take a measurement. I'll zoom in a little bit, and I'm going to adjust the cursors just to try and get steady state. And so we can see for the instruction of UINT8_t, and for the operation of just passing the number, I'm getting a time delay of about 1.8 microseconds. So now what I'm going to do is go back to my code, and to show a different operations, instead of num, I'll do num times 3, and I will keep this as an unsigned integer 8-bit. So now what's going to happen is I'll come back here and I'll run my oscilloscope, so it's actively running. I'll come back here, I will run my code, come back to the LEDs, it should cycle 3 times and then do the test function. Once, twice, and it's going to count one more time. There we go. And now that we go back to the scope, you can see that I haven't moved my cursors, but the time to execute the arithmetic function, which has changed from just num to now num times 3, so we're performing a multiplication arithmetic. You can see that already it's taken longer to execute this arithmetic. So what I'm going to do is hit stop, and we're going to measure the time delay. I'm going to move this cursor to about steady state. And if we look here, 2.7. So that was about twice as long to perform that arithmetic. And this shows my whole test setup. What's basically happening is the user can specify what data type they want here. It will be set for all instances that regard test function and any variables related test function. The user can then specify what arithmetic operation they want to perform. The LEDs will count to 15 in binary, lighting up the LEDs 3 times, and then it'll go into the test function operation involving PC0 and PC1 turning on and off. And I'm taking measurements with my oscilloscope, and I'm using the steady state time delay between high and low of my channel 2, which is PC1, which again references the arithmetic function, to determine the time delay, or how long it takes for the software or the hardware to execute that arithmetic.